In this video, we're going to go over notes 6 and 7 of the thermodynamics unit, and a lot of this information is going to feel very familiar, and that's because you've probably seen it before. But what we're going to do is in note 6, we're going to take those graphs with activation energy and whatnot from the kinetics unit, and we're going to do the same thing, except we're just going to show you what sort of thermodynamic information can be gathered from these graphs. And then in note 7, we're going to do Q equals MC delta T, and then ultimately we're going to turn Q into delta H, okay? Because Q in regular chemistry, that was just heat, and then delta H is specifically the change in heat in units of joules per mole. Okay, so let's get started. So we have a graph like this, and I'm going to write in a couple different colors just to make this easy. This graph needs to overcome this energy barrier called the activation energy, and this is specifically the activation energy for our forward reaction. We start here, we end here, and if I draw a straight line, or as close to a straight line as I can see that I end up losing some energy. My energy ends at a lower place than where it began. Additionally, all reactions, they can go backwards. If I ended up going backwards, which would be like from end all the way to start, this would be my activation energy for my reverse reaction. We know that we lose energy here. If we're talking about the forward direction, we lose this much energy, and so we would call that exothermic. And so this value that I have in blue here, this would be my delta H, and delta H would end up being a negative number. Okay. Now, at the very top of our peak, this is called the transition state. This is also called the activated complex, and that's where bonds are being broken and formed simultaneously. Okay, now, same sort of graph, just a little bit different between where we start and where we end. So we start here, we end here. We have our activation energy for our forward reaction. And then we also have our activation energy of our reverse reaction. Here, we end at a place much larger than where we started. And so this would be called an endothermic reaction. In an endothermic reaction, our surroundings actually get cold. And that's because our system absorbs heat from the surroundings. Okay, now between where we started and where we ended, this would be called delta H, and that would end up being a positive number because we're endothermic here. Additionally, the top of our peak, we'd call that the transition state or the activated complex, and that's where bonds are being broken and formed simultaneously. Okay, this is all summarized here. We see activated complex, bonds broken and formed. Okay. Now, these are just some old AP questions. It says, what distance corresponds to the activation energy of X? Here, X going to Y. And the activation energy of X going to Y, that looks to be just letter B. It's how much energy does it take to get to the top of your peak to get to your activated complex? So this first question, that would be letter B. And then what about enthalpy? Enthalpy is delta H, and that would be letter C or letter A. It's kind of confusing why they have both on here. Okay. Now, in part B, this was a multiple choice question. It says, what value represents the enthalpy for the following reaction? It won't be 1. It won't be 2. This is EA forward for 1. This is EA reverse. And it'd actually be number 3. This is delta H. And if they asked, this would be an exothermic reaction. Okay, let's go over notes 7. This is going to feel very similar. Just hang tight with me and make sure you're doing the calculations. So you want to have a calculator out with you, because most of the time, any issues I see on a test or quiz with heat transfer is just a calculator error. So heat always flows from the substance with the higher temperature to the substance with the lower temperature. That's just laws of nature. So what impacts how much the temperature is going to change of a substance? It depends on how much heat is being transferred. Heat has the symbol Q, and is typically measured in joules, although sometimes you do see it in kilojoules. It depends on how much of the sample you have. Mass is typically going to be measured in grams, and mass will have the unit M, so that'll be grams. And then it depends on the identity of a sample. So, for example, metals, whether that be like copper or iron, things that you might cook with, those absorb heat really, really easily. Whereas other things like styrofoam or even like clothing necessarily, like cotton, they don't absorb heat as easily. And so depending on what your use is for something, you might choose different materials. But that's going to be the specific heat capacity. Okay, so that's going to be the specific heat capacity. And that's where the C comes from. And I'm going to go down here to specific heat, letter C. And if you remember, like water has a specific heat of 4.184 joules divided by grams degrees Celsius. What that means is if I wanted to change 1 gram of water by 1 degree Celsius, I would specifically need 4.184 joules. Okay, so what we're essentially doing is just converting here. Calorimetry is the process used by actually measuring how much heat is lost or absorbed by a system. And what we do in lab is we tend to have like 2 styrofoam cups. So if you look at this picture, we have 2 styrofoam cups. Styrofoam is an insulator, meaning that it doesn't really absorb heat or release heat well. And we have a thermometer where we can measure the temperature change. And what happens is, based upon how much your water or your surroundings changes temperature, that'll give you a clue into what your system is actually doing. So for example, if we have a reaction between, I don't know, calcium carbonate and nickel, just let's say that's a reaction, my thermometer is not actually going to be able to enter the system. My thermometer will be in the surroundings, and so based upon what my thermometer does, I'll be able to make some assumptions about my system. Okay, so you may remember this. Q equals MC delta T. Q will be joules. M is going to be grams. C is specific heat capacity, joules divided by grams degrees Celsius. And then T is almost typically in degrees Celsius, although technically it could be in Kelvin and it doesn't throw off the math. So delta T is going to be T final minus T initial. Okay, and sometimes we need that. Okay, so I have some steps here. You're welcome to read through them, but I'm going to go ahead and just get started. So the first type of question we have is solving for Q. So here we have a 445 gram sample, of ice, and it's at negative 58 degrees Celsius, so that's some sort of temperature, and it's heated, okay, that's an important thing, it's heated until its temperature reaches negative 29 degrees Celsius. We want to find the change in heat of our system. The specific heat of ice is 2.05 joules per gram degree Celsius. You may be wondering, Mr. Payne, you said water has a specific heat of 4.184, and what I probably should have said is the specific heat of liquid water is 4.184. If we're at solid water, which would be ice, our particles are going to be arranged much more closely, and so chances are it's not going to take as much heat or as many joules to actually heat up those particles because they are closer together. Okay, so our formula is Q is equal to MC delta T. Q is our change in heat, so that's what we're going to be solving for. Q is equal to 445 grams. Specific heat of ice is 2.05 joules divided by grams degrees Celsius. Our delta T is T final. It's negative 29 degrees Celsius minus T initial, which is negative 58 degrees Celsius. I'm going to plug that into my calculator just how it is. And when I do, my calculator is in scientific notation as I do this. It is 2.65 times 10 to the 4th joules. Okay? Pretty straightforward question, I would hope. Now, in part B, we're going to be solving for something besides Q. So we are going from negative 34 degrees Celsius to negative 3 degrees Celsius. So this is we're heating. And if I want to just flip back to part A, notice I heated, and when I heat something, Q should be positive. Okay, because our system is absorbing heat. So that is exactly what I see. So again, here our Q should be positive, and it says our sample absorbs 1.41 times 10 to the 5th joules. We want to find the mass of the sample, and again, the specific heat of ice is 2.05 joules per gram degrees Celsius. So our formula is Q equals MC delta T. Our Q is 1.41 times 10 to the 5th joules. That equals our mass, which we don't know right now, times 2.05 joules divided by grams degrees Celsius. Our final temperature was negative 3 degrees Celsius, and our initial temperature was negative 34 degrees Celsius. I'm going to go ahead and multiply those two numbers in parentheses. And when I do, I get M times 63.55 equals 1.41 times 10 to the 5th. I'm going to divide each side by 63.55. And then I'm going to take 1.41 times 10 to the 5th, divide it by 63.55, and I get 2218.7 grams. Now, let's say, and I know it doesn't say here, but I want to solve for it this way. Let's say we had a second part that said convert to delta H. Okay, that's not going to be really overly tricky if we understand one formula. Okay, delta H is going to oftentimes be represented in kilojoules per mole, but I always like to change it to joules per mole. If we can get behind that, then we have the formula that delta H is equal to Q over mole. And our Q here is 1.41 times 10 to the 5th joules. We just need to figure out the moles of ice that we have. Well, I just solved for the grams, so what I'll do is I'll take 2218.7 grams of solid water, which is ice. Hopefully at this point in the year you have the molar mass of water memorized, and 1 mole of water is 18.02 grams. And when I do that, I get 2218.7 divided by 18.02. and I get 123.14 moles of H2O. So 123.14 moles. 1.41 times 10 to the 5th divided by 123.14, and I'm going to get 1145.18 joules per mole for delta H. Let's see if this makes sense. We are heating our substance. We're increasing its temperature, going from negative 34 degrees Celsius to negative 3 degrees Celsius. That is an increase in temperature. Therefore, our delta H should be positive. So that makes some sense to me. Okay, now this is probably the hardest math of this unit just because you got to get every part right. So we'll do this example. Your skill set has these examples, and then we'll do one other example. Okay, then we'll call it quits on this. So what happens when you mix hot substances and cold substances? Hot substances and cold substances will keep exchanging heat until they reach the same final temperature. Okay, so hot and cold substances, they mix until they reach the same final temperature. And this is called the thermal equilibrium. Okay, and so what we need to understand is that when a hot substance comes in contact with a cold substance, that hot substance is going to lose some of its heat energy to the cold substance. And so my hot substance is going to have a negative Q. Okay, it's going to be an exothermic process for that hot substance. On the flip side, my cold substance is going to be absorbing heat. Okay, it's an endothermic process for my cold substance. Okay, so imagine if you had hot chocolate, and to cool it down, you put some ice cubes in it. The ice cubes would be my cold substance. They're going to be absorbing heat from that hot chocolate, whereas my hot chocolate's going to be giving off heat to my ice cubes, okay? Until, though, they reach the same final temperature. So we have 175 grams of hot aluminum. It must start off at 100 degrees Celsius, and it's dropped into an insulated cup that contains 40 milliliters of ice-cold water. Okay, we need to determine the final temperature, X. The specific heat of aluminum is 0.9 joules per gram degree Celsius. The specific heat of water is 4.184 joules per gram degree Celsius. Okay, so I'm going to write my formula. M hot, C hot, delta T hot equals M cold, C cold, delta T cold. And my hot substance is aluminum. My cold substance appears to be water. And most, maybe 95% of the time, your cold substance is actually just going to be water. So what's the most common mistake is, I want you to make a note here. Don't forget that negative. Okay, because that's going to throw off your math. So my hot substance mass is 175 grams. Okay, I got that checked off. I'm getting the specific heat of aluminum. That's 0.9 joules per gram degree Celsius. My delta T, they don't tell me the change in temperature, but they do say that it starts off at 100 degrees Celsius, and I'm trying to find the final temperature. This is the final temperature for both aluminum and water, for the same reasons that we had talked about. They mix until they reach the same final temperature. So I'm going to be solving for T final. The mass of my cold water, they don't directly tell you, but if you remember that the density of water is 1 gram for every 1 milliliter. And so that means that 40 milliliters of water will be 40 grams of water. The specific heat of water is 4.184 joules per gram degree Celsius. final temperature of water is something that we're solving for, since both the aluminum and the water will have the same final temperature. And we started off at ice cold water, so it was literally at 0 degrees Celsius. Okay, so what I'm going to do is I'm going to multiply these guys. And I'm going to change that variable TF just to X. For some reason, I like it better that way. I get negative 157.5 X minus 100 equals 40 times 4.184, 167.36. And then TF minus 0, that will be the same thing as X. Okay, there's a lot of math you can do here, and those of you that have a TI Inspire, you can fast forward to the final answer because you have a calculator that just solves this out. But I want to talk through the math just to make sure we all understand. I'm going to go through the options that I see, and hopefully I won't miss any. You could distribute. I probably would not do it that way, but if you wanted to distribute, you could do that and then combine like terms. Or what I see is we can just divide each side by negative 157.5. Or we could even divide each side by 167.36. Okay, either of those methods is going to work. I tend to like divide by 157.5 negative. So I'm going to get X minus 100, because those will cancel out. That's going to equal 167.36 divided by negative 157.5. I get negative 1.0626x. I'm going to combine like terms, so minus x, I get over here negative 2.0626x equals negative 100, divided by negative 2.0626, divided by negative 2.0626, and when I solve that out, let me just plug it in. 100 divided by, I get 48.48, so I'll round it 48.5, and the units on that, because that's temperature, will be degrees Celsius. Okay, last question here. And here we're just going to talk about converting Q to delta H. So again, very similar. So if you want, go ahead, pause the video, try this one out on your own. I'm going to end up solving it. But if you can pause it and do it, then I say you're probably in really good shape. Okay, so it says calculate the heat necessary to change the temperature of 1 kilogram. Okay, we need grams, most likely, of iron from 25 degrees Celsius to 1,000 degrees Celsius. The specific heat of iron is 0.451 joules per gram degrees Celsius. So Q is equal to MC delta T. We are solving for heat, so we're solving for Q. That's equal to 1,000 grams. Specific heat of iron, they tell us, is 0.451 joules per gram degrees Celsius. This makes a lot of sense to me. Water specific heat's 4.184. Water, if you own a pool or you've been in the ocean on a hot day, you know water's a really poor conductor of heat. That's because in its formula, it doesn't have a metal. Okay, where on the flip side, if you've ever felt like a stone building, typically a stone building will have limestone in it, and stone gets really hot on a summer day underneath, sitting in the sun all day, and that's because limestone is made up of calcium carbonate, and calcium is a metal, and so that helps that calcium carbonate absorb heat really well. Well, iron is just a metal, and so that it should have a low specific heat value, because a low specific heat value means that that substance absorbs heat really well. Okay, our final temperature is 1,000 degrees Celsius. Our initial temperature is 25 degrees Celsius. When I solve for Q, I get 439,725 joules. 1 joule is a very, very small amount of heat, so you always sort of expect at least 1,000 joules. So we need to convert Q to delta H. If you remember, delta H equals Q over mole. We know Q is 439,725 joules. We just need to get the moles of iron. We have 1 kilogram of iron, so that's 1,000 grams. There's 55.85 grams of iron in 1 mole of iron. Divided by 55.85. We're going to get 17.91 moles of Fe. 17.91 moles. We divide them and we get 2.46 times 10 to the 4th joules per mole for delta H. Again, should be positive. This is an endothermic process. I know this because the temperature of our system is increasing.